We're surrounded by all these smart devices, but have you ever really stopped to think about what makes them, well, smart? Today, we're going to pull back the curtain on the real unsung hero of all our electronics, the mighty microcontroller.
I mean, really think about it. You hit 2, then the plus sign, then another 2, and then equals. And boom, a 4 just appears. It's something we totally take for granted, but what is the magic happening inside that little plastic box to make that work? Every single time, without fail.
Well, the answer is this little guy, a microcontroller, or MCU for short. The easiest way to think about it is as a whole computer, but shrunk down onto one tiny single chip. Now, it's not going to run your video games or anything. It's not a powerhouse like your laptop's processor. Instead, it's designed to do one specific job and do it absolutely perfectly. It takes an input, like you pressing a button, follows a set of instructions we give it, and then controls an output, like showing a number on a screen. Okay, so theory is great, but let's make this real. To really get a feel for how an MCU works, we're going to walk through the plan for building a simple little calculator.
All right, now this might look a little intimidating, but don't worry, it's just an electronic blueprint, a schematic. Over on the right, that's our keypad. That's the input. The LCD screen, that's our output, where the answers show up. And that chip right there in the middle, the PIC16F87, that's our guy. That's the microcontroller. It's like the central nervous system physically wired up to listen to the keypad and talk to the screen.
But of course, the hardware is only half the battle, right? We have to give that MCU a recipe to follow, a program, and it's actually super logical. The MCU just sits there and waits for you to press the first number. Then it waits for the operation, plus, minus. Then it waits for the second number. As soon as you hit that equals key, it does the math, sends the answer over to the display, and then wipes it clean, ready for the next problem. It's just a simple, clear set of instructions.
So here's the cool part. How does it actually know which button you pressed out of all 16? It's a really clever trick called scanning. Imagine the MCU sends a tiny little electrical pulse down the first row, then the second, then the third, over and over, thousands of times a second. At the same time, it's listening on all the columns. So when you press a button, let's say it's the number 5, you're physically connecting its row to its column. The MCU instantly detects that connection and basically goes, aha, I sent a signal down row B and I just heard it on column 2. That's got to be the 5 key. Pretty smart, huh?
So we can see that MCUs are awesome at handling our button presses, but they have another superpower, something even more fundamental. They have an incredible sense of time. So let's shift gears and see how that unlocks some even cooler possibilities. Okay, imagine you need your program to just wait for exactly 1 second. Now, the simple way is to tell the MCU to just count to a big number, kind of like you counting 1 Mississippi, 2 Mississippi in your head. It works, but while it's doing that, the whole program is frozen. It can't do anything else. The much smarter way is to use a built-in hardware timer. This is like setting a tiny, super precise alarm clock that's separate from the main brain. Your main program is totally free to go do other jobs, and when that 1 second is up, the alarm goes off and tells the program, hey, time's up. It is just so much more efficient. This awesome feature actually has a name. It's called compare mode. Here's how it works. Deep inside the microcontroller, there's a special counter that's just always ticking up super fast. All we have to do is tell the MCU our target number. We load it into a special little memory slot. The hardware then just constantly compares the ticking counter to our target number. The very instant they match, boom, it triggers an event. It can be anything like flipping an LED on. And check this out. This simulation shows you exactly what that looks like in action. In this example, an MCU is using that compare mode to create a perfect 100 Hz signal, and the proof is right there on that virtual oscilloscope. Just look at how clean and perfectly regular those pulses are. That is the beautiful precision of a hardware timer. You could never get a signal that clean just by counting in software. Okay, that's really cool. So we can use these timers to create signals with incredibly precise timing. But what if we wanted to flip that idea on its head? What if we want to measure the timing of a signal coming in from the outside world? Well, for that, we use another amazing feature called capture mode. This essentially turns the MCU's internal timer into a ridiculously fast stopwatch. The timer is just running constantly in the background, ticking away. But when some external event happens, like a pulse of electricity hits one of its input pins, the hardware instantly captures the exact value of that timer, right at that nanosecond, and saves it. It's like a photo finish at a horse race.
So here's the setup for that. On the left, we've got a virtual signal generator that's just sending a steady square wave into our MCU. The MCU's only job here is to measure the time between each of those pulses. And to do that, it uses capture mode. It grabs a timestamp on the first pulse, then grabs another timestamp the moment the next one arrives. And the difference between those two capture times, that's the exact period of the signal we're measuring. So here's how the program's logic flows. First, that incoming pulse triggers an interrupt. It sends up a little flare to tell the chip, hey, something just happened. At that exact same moment, the capture hardware saves the current timer count. But that's just a raw number, right? So the program's main job is to take that number and convert it into digits a human can actually read, just like our calculator did. And finally, it sends those digits off to the LCD screen, showing us the period right down to the microsecond. So, let's just take a step back. We started out just doing simple math, and now we're accurately measuring time down to a millionth of a second. It's a pretty quick tour, but it's a peek into this incredible hidden world that's humming away inside all of our electronics. And just think about what we just saw. Using the exact same little chip, we've built 3 totally different things. We made a calculator that listens to a person, a pulse generator that creates its own perfect timing, and a measurement tool that can analyze a signal from another machine. That is some serious versatility packed into one tiny piece of silicon.
And it's so important to remember, this isn't just a fun science project. These abilities, reading inputs, doing calculations, and precisely controlling and measuring time, these are the absolute fundamental building blocks of almost everything we use. The complex controller in your car's engine, the simple keypad on your microwave, even life-saving medical devices, they all rely on these exact same principles, just on a much grander scale. So that really leaves us with one final thought. Just take a look around you, wherever you are right now. Your phone, your TV remote, your coffee maker, maybe your watch. How many of these tiny, silent, invisible brains are working tirelessly, right now, calculating and timing things to make your world run? I guarantee you, the number is way, way higher than you think. Thanks for diving in with me.